Mathematics, as we all know, is a quiet and solitary discipline, unless, of course, David Abrahams is involved. For nearly 40 years, David has been the human whirlwind at the heart of UK applied mathematics. He has been energising institutions, mentoring generations of young mathematicians, and somehow managing to charm both pure and applied camps into playing nicely together, which is either a miracle of diplomacy or some very well-placed northern charm, or, perhaps both. If you have met David, as I imagine everybody here has, you will know that he is relentless, irrepressible, and maddeningly effective. He's also one of the most generous champions of our community that our community has ever had. He has held two of the most important jobs in UK mathematics, director of both the ICMS and the Isaac Newton Institute, and he's brought new life to both of them. When COVID hit, he turned INI virtual almost overnight and helped set up a knowledge exchange network that won an award because, of course it did. And that is before we even get on to the mathematics itself. Waves, acoustics, electromagnetism, meteorites, glaciers, financial markets, you name it, David has published on it. He is basically the applied maths answer to David Attenborough, just with slightly fewer cameras and way more partial differential equations. For his extraordinary service to our community, I am absolutely delighted to present the IMA's highest and honestly most bling honour. Oh, look at that. That's extraordinary. The gold medal to Professor David Abrahams.
Thank you. Josh. Very much. Chef Nick and Walsh.
David, over to you.
Thank you.
Here is yours. Thank you.
Thank you very much. Well, it feels like my funeral. Really does. Thank you very much. That's very kind of you. So I have to put in the apologies first. And thanks, of course. Thanks, Hannah. Brilliant you're here. What a champion of mathematics you are. You put us all to shame. But you're at Cambridge now. It's fantastic. So we're hoping to use her mercilessly for everything. So really, thank you very much to everyone in this room, everyone I know well. And you've been incredible champions for our community. And the talk today is going to be about our community, about applied mathematics. And I want to ask a few questions of you, but I don't have time to get any answers from you. So, but before I do that, thank you very much. It's actually been 46 years since I started my PhD. 46 years, and I've loved every moment of it. My first conference was in Cambridge. I had terrible toothache for the whole time, got drunk, obviously, to compensate for that, and I've never really ever thought of doing anything else. It's been fantastic. So the talk is going to be historical, and I hope to pick out figures who could represent applied mathematics as I would see it, as really in all its glory. I've got some of the history, but no time to talk about their contributions. So I apologize for that. So in some sense, maybe you can listen to me again. Right. Applied maths in a changing world. Let me just see if there's anything else I want to say. I looked at my abstract and Lynn spotted that my abstract is sufficiently vague that I can say anything. But basically, I've tried to stick to it. And I did put in a few excuses that said it's highly selective, narrowly researched, and somewhat opinionated. And I think those bits hold true, certainly. So it's my version of applied mathematics as I see it. Where did it come from? Where we're going to? And what are the important aspects of it? Let's ask some questions to start with. So, questions. What is applied mathematics? We're going to talk about applied mathematics in a changing world. I think we all know what a changing world is, but what is applied mathematics? It's not easy to say. I'm not going to let you answer now, but more generally, what is mathematics? So if we know what applied maths is, or we have a picture, what's the bigger picture of what pure is and how does it fit into it? So they sound trivial and obvious, but the more you think about it, they sort of disappear into nothing. What is not applied mathematics? When is an engineer and not an applied mathematician? And I've sort of struggled with these questions over my career to recognize what I am and what I'm not. And when did applied mathematics begin? So where can we trace its origins? The expression has been used, but in what context? How do we interpret it? And then, what is the purview of applied mathematicians? What are we allowed to study and what we're not? So if we can't get our work published in any journals that we would recognize in some sense as being part of our community, then we're sort of failing, perhaps. And who decides what applied mathematics is? And with our community, we often try and implicitly make those assumptions of what it is and not what it isn't. And then important people come along and they say what it is. REF comes along, the landscape documents which define it. So they're hard questions. And here's a question. Is this man an applied mathematician? Anyone tell me who he is? Yes. Well done. Norbert Wiener. I don't know how he was American. So he was a fantastic individual, and many of you know him. But let me just give you a quote that's in MacTutor, the St. Andrew's collective of information about past mathematicians. It says that in appearance and behaviour, Norbert Wiener was a Baroque figure, short, rotund, and myopic, combining these and many qualities in extreme degree. His conversation was a curious mixture of pomposity and wantonness. He was a poor listener. His self-praise was playful, convincing, and never offensive. He spoke many languages, but was not easy to understand in any of them. And he was a famously bad lecturer. So there's a million ways to skin the cat, isn't there? You can do it. He was a brilliant figure. He was always bitter and twisted that he never went to Harvard. He had to end up in MIT. He was in an engineering department, and he was stimulated. His research was fantastically informed by his conversations with engineers. So to me, he is a quintessential applied mathematician. If you'd asked him, he'd probably said he's an engineer stroke pure mathematician, maybe. But for those of you who recognizing it, Raphael and David at the back, this is just Fourier transforms, and there's plus and minus functions, so they're half range for. This is the essence of Wiener-Hopf technique built in here, but this was for the Wiener filter in signal processing. Okay, some more questions. So when I'm thinking about applied mathematics, should I include much more broadly OR, stats? Are they part of the canon of applied mathematics, medical, industrially? And then what do applied mathematicians actually do? Yeah, we get paid for some reason, and what we do. Should we be talking to industry more? Should we do ethereal problems? Is our role relevant? What's the future? Will I stop asking questions and get on with it? Okay, so let's get on with it. So let's answer this question. What differentiates applied mathematicians from physicists, engineers, pure mathematicians, and others? So try to mesh some of those questions into one. And let's see what Perplexity, which is an AI bot, comes up with. Sorry, it's dense, the text. And I apologize that my slides are all far too busy. There's too much stuff in any of them. I got far too many. And I'll just blast through them as quickly as I can. So I've highlighted in yellow, which is hurting my eyes. And this is what it says. I hope you're reading it. And let's see if we all agree with this. While their work often overlaps with that of physicists, engineers, blah, blah, and other professionals, applied mathematicians maintain distinct characteristics in their approach, methodology, and professional focus. This distinction lies not only in their specific skill sets, but also in their fundamental perspective on mathematical problem solving, their relationship with the theoretical frameworks, and their approach to real-world applications. Do we give that a tick so far? Yeah, it's pretty good. A specialized discipline that combines rigorous mathematical methodology with interdisciplinary collaboration. Yeah, it's pretty good. More. The objective is not only to intelligently apply existing mathematical tools and insights to solve scientific problems, but also to develop novel and useful mathematics inspired and driven by the applications. Again, not bad. And then this one is for Chris Budd here. Mathematical modeling serves as a cornerstone of applied mathematics, representing a method that uses mathematical language to describe the behavior of the real world systems. Blah, blah. Yeah. So I think, have they missed anything? No, we're all on page. Okay. So let's think about cultural attitudes before I start going through some history. So make a case in my talk for when applied mathematics emerges as a distinct discipline. Different countries have a very, very different attitude to applied mathematics, what it is and what it does. How it fits into the whole mathematical sort of canon, cultural differences, and then largely I mean British style applied mathematics. I put in Norbert Wiener at the beginning, but we count him as British, shall we, for this purpose of my talk. And it has a really rich heritage, and that's what I'm going to try and describe today. So on to the story. So let's think about the world. It says it's a changing world. So what we got? Tensions between world powers. Tariffs versus free trade is a particular one that we may focus on. Tensions, wars, Ukraine, Middle East, lots of other ones. We're in the middle of huge environmental and health crises. And then we have the war of culture, which is all around us. At universities, under threat. Truth, under threat. Religion versus science, that debate of whether one is, in some sense, to be used rather than the other. Social, racial, gender inequalities, and the pushback on those. Rampant changes to society due to new technologies. And probably that's what you thought I was going to be talking about in this talk, about all the new technologies. And of course, immigration and global disorder. Anyone think I've missed anything out? Okay, but I'm not talking about now. I'm talking about the 1850s to the 1900s, the Victorian era. Those are exactly the same issues that they were facing. So tensions between world powers. Then it was Britain, the British Empire, and there were lots of other countries. So Britain had a desire for free trade, openness, no tariffs, and other countries were trying to impose that. So we had all of that. Tensions, Ukraine, but it was Russia's annexation of the Crimea. Palestine was a trouble spot as well in those days. Environmental and health crisis, we know with industrialization came with it huge problems, social problems, economic problems, and environmental problems with the emerging cities. And of course, there was a huge culture wars. And one of the main parts of my talk will be to discuss the culture wars and Oxbridge versus the civic universities. Of course, big business, etc. But I'm going to focus on that first point. Social, racial, gender inequality, of course, was enormous. And then the rampant changes to society, of course, it was steam, energy, availability, railways, telegraphy, electricity, huge changes in society. And of course, immigration. But the immigration was from the rural areas to the cities. Okay. So just to comment before we get into this story, the Victorian era was a period, I think you could argue, of greater change than anything we've seen in the second half of the 20th century and into the 21st. Maybe AI will change that, but enormous change. And academia always both reflects and drives that change. And I think this was the case, and we want to show that story. And it's arguable that the Victorians were smarter than us. And then believe it or not, in doing my investigations, I came up with this paper from 2013, so 12 years ago. Were the Victorians cleverer than us? And they did it that intelligence goes with reaction time. So how quickly you react. There's meant to be a correlation which is evidence-based, and they looked, somehow there were records from the Victorian era now, and they found that we've declined in our reaction times. So that was the conclusion. But I think we can't just write them off as people do. And what have the Victorians ever done for us? What's their impact? Why are we talking about this? So I've become hugely interested in the Victorian era, and I've bent loads of people's ears off about it for quite a while now. And it's because I grew up in Manchester, and my brother's here and we grew up in the sort of after effects of the Industrial Revolution. It was all around us, the decay, the sort of horrors of it all were facing us. And we didn't then ever focus on the interesting side, the history, a little bit, but it just seemed very much something you wanted to get rid of. And Manchester's unrecognisable today as it was. So place of birth is very interesting. My age, and I've said this to other people, as you get older, your metric to measure things is your age. I'm 67. So if you go backwards from when I was born, you go back to 1891, well into the Victorian era. So it's very real to you because it's just one lifespan ago. And that analytic continuation of the past is a very good way of thinking about it. And of course, its influence on its society as we recognise it today. And the birth of British style applied mathematics was wrapped up into this. And of course, Sherlock Holmes. Okay, so Sherlock Holmes, fascinating. We all love him. And we all know, is it Paget? I don't know how you pronounce it, but Sidney Paget was the illustrator for Sherlock Holmes, gave him the Deerstalker. And then J.J. Thomson, who many people will know, a brilliant physicist, but we'll come back to that later. His father-in-law was George Edward Paget. And I just wondered whether those two were related, as you do now. So you ask your favourite software. I didn't even go past it, I just Googled it, and Gemini tells you the answer. It says George Edward Paget and Sidney Paget were brothers. It then tells you on that. But of course they weren't. They were separated in years by 51 years in their birth date. Unless he remarried, it wasn't really possible. So you can see the dangers of the AI tool are there, present for all of us. You can easily fall into black holes because AI is doing something quite different from all the other tools that we've used as mathematicians. So maybe we'll touch on that later, but it's a good story anyway. So here's the story as it really begins. So some of the protagonists, and let's see who can recognize any of them. Yeah, well done. Sorry? It is indeed well done. 2 out of 2. Horace Lamb. Yeah. You're cheating. Okay, Horace Lamb, we have that picture of him. It was hand drawn by his son, Henry Lamb, who's a very famous painter. Far more famous in broad circles than Horace's father was, or is. Anyone else? Lord Rayleigh. Second left is Lord Rayleigh. You know, this guy, heavy side, very good, heavy side. So an unusual character. And what about these two down here? So this is Arthur Schuster. So you'll know him from Manchester people. So the Schuster Laboratory in Manchester. He was a physicist, but we'll talk about him. And that's Osborne Reynolds, also from Manchester. And then the top left is Charles Bayer, who was and he was a key figure in the setting up of Manchester University. So we'll come back to him. So those are our protagonists. So I'm going to try and go through this as quickly as possible. So just scene setting. What were Oxford and Cambridge doing? So they were educating gentlemen for a life of running the country, for the church, for royalty. They were part of the gentry. They were seen as people who needed a good education. And later on, they started going into gentlemen's professions, banking, city politics, etc. But in the 19th century, even the second half of the 19th century, Oxford and Cambridge were not seen as places to educate the elite in industry or anyone from industry. That was a sort of dirty subject, nor for industrialists to become part of the Oxbridge elite. There was a separation in roles, a recognition of what the role or the function of the universities at that time was. Now, I'm paraphrasing here, and others may completely disagree, but this is broadly, I think, a reflection of that. The curriculum was dominated by classics at Oxford and mathematics at Cambridge and theology and other subjects. And the tripos at Cambridge had a load of subjects, and it became dominant mathematics because it was seen as it was properly examined, and you could then rank yourself against your colleagues. So it became the first sort of traditional university sort of subject that was properly discriminated and assessed. Before there, it was very gentlemanly, the process of getting your degree, etc. They were teaching focused. Research was not a requirement for fellows. Entry was restricted. Religious conformity, landed gentry, wealthy, so you had to have plenty of money to go there. And there was a strong reliance on private tutors who in turn influenced the curriculum. So we had these private tutors who would take the students, put them through their paces, train them to pass the exams, and they themselves had a hand in defining the curriculum. But it was successful, as we'll see. And Scottish universities were doing similar things. So that was the second half of the 19th century. The Victorian era was a time of incredible industrial change, but Oxford and Cambridge were somehow slow to change. And then, thanks to Chris Linton here, he pointed me to this book, Mr. Hopkins' Men, written by Alex Craik, who was an applied mathematician. And he wrote this book, and then this is an early picture of Thomson. And you can see the caricature of these individuals. They were very much gentlemen, scholars, and they came in and then went out and led the world. Okay, a very, very different picture of what education is about in the civic universities, which were fighting to come into existence. So the Industrial Revolution, you all know this, so I'll flash through this, but of course we know it's slow changes through to the sort of 1850s, and then the canals came along and shifting of goods, etc. Rapid shift from handcrafts, labour-intensive agriculture and other industrial processes to machine-based manufacturing. Economics, political, legal changes, free trade, as I mentioned, access to investment, income, etc. So there was this huge opportunity suddenly available, and people took advantage of those opportunities. Technical innovation was really supported, mass production, urbanization, etc. And Manchester became the first industrial city, epicenter of this, because its positioning, access to the docks, coal, water, transportation, etc. And it had a booming textile industry, innovative and entrepreneurial culture, as we'll see in a minute, and growing population. Okay, so before the Victorian period, then we had these industrialists who we all know to this day: Watt, Stevenson, Brunel, Arkwright, Telford, Wedgwood, others. There were none of them university educated. They were wealthy but knew money, industrial money, and they were then trained. How were they trained? Well, on the job. Training passed on through an artisan class, immigrant workers coming in with skills from other countries, apprenticeships. So there was a recognition there was needed a new approach. They knew that in order for their products to get better, for boilers to stop blowing up, they need to know about metallurgy, fractures, making materials which were not brittle. They needed to know about money supply, economic theories. They needed to know about lubrication theory to stop the engines from fouling up. Okay, all of these practical things, they recognized there was a need to turn them into from ad hoc engineering into a science. And that was that those thoughts were taking place, and there was a need to sort of bridge the gap. So what happened was the birth of the Mechanics Institutes, but more broadly, lit and fill societies were growing up everywhere. So it was about culture change, not just feeding industry and making industry work for you. And it was a melding of those two which were influential. Okay, but lesser known elements of the Industrial Revolution. Manchester became a magnet for German merchants and industrialists. They brought with them industrial expertise as well as cultural and educational values. Okay, strong emphasis on education and civic responsibility. So highly educated, valued academic achievements, scientific research and culture. So Manchester became this sort of cosmopolitan world, intellectually vibrant. We know that Engels lived in Manchester because he found that stimulated. He could analyze the way society was changing, etc. And then they brought with them the Humboldtian model of universities as places for teaching and research, and on original research, and encouraging students to think of a pathway through their studies rather than being told this is the curriculum, academic freedom, and a broader secular or non-denominational middle class. So to cultivate autonomous individuals and world citizens. So not just people being trained to be elite. Okay. And in Germany, universities had significant autonomy despite state funding. So we have this idea that Manchester and other northern universities were sort of building up ahead of steam. So industrialization, they needed a well-trained, advanced thinking a community of workers, designers, etc. And the motivation was not purely economic. It was driven by, a sense of making the world a better place, promoting social mobility. And civic universities emerged as seen as crucial engines for regional economic growth. So the feeling of people in Manchester and Birmingham and all the other northern cities was that they needed something which wasn't just the Mechanics Institute or a lit and fill society. Okay. And that last one there, they started thinking in terms of partnerships between civic authorities, local industrialists, philanthropists. Okay. So here's an article from The Spectator in February the 9th, 1867. So I'm going to show you when Manchester sort of began, but it's called the University of the Busy, in contrast to the University of the Idle. That's what it means. Okay. And it's saying it really got going. They'd had several previous attempts which had fallen on their nose. And they were finally getting people like Bayer to give serious cash. Okay. So Victoria University, 1851, Owens College became part of a federal university structure. Liverpool, Leeds and Manchester formed this federal university in 1880. And you can see the politics of work. The people in Parliament hated this idea. Oxford and Cambridge hated this idea. All of the northern cities wanted their university, and they were all clamouring to kill everyone else's off. So there was, had to be an act of Parliament. And in the end, the compromise, the three places, as soon as it became a federal university, all three places were trying to separate and become on their own. And Manchester finally made it in 1904, but Birmingham had slipped in underneath and made it earlier, etc. And in 1881, this guy, Bayer, he gave a legacy to the university, which was very large in those days, and and it set up two chairs, one in applied mathematics, other one, which some people say was engineering, others economics. We don't know. It sort of disappeared, but the applied maths chair is still alive and kicking, and now Paul Glendinning holds that chair. Okay, but let's go back to Cambridge. So mathematics at Cambridge is seen as the keystone of natural philosophy. And natural philosophy is understanding the universe, and it encompasses both the abstract mathematical world and the physical world. Say two halves of the same universe. So maths and physics somehow were intertwined, viewed very strongly through Newton and other very big scientists, influencers. So light, sound, heat, materials, motion were studied. They were part of the curriculum. They were thinking about that. Continuum theories were but it was just how they were applied and what was the way they were thought about. It really was about viewing them as about discovering God's will in some sense rather than practical application. But Cambridge was already changing. It's wrong to say that Oxford and Cambridge were stuck in the past. Not true. So Cavendish Laboratory opened in 1874. The engineering department opened in 1875. An engineering department in 1875 in Cambridge. But they sort of managed not to do much engineering that was really dirty stuff. It was quite clean. And we know that maths didn't manage to get its act together to get a department at all. And when they got one, they got two. And they still got two. So never managed to sort of solve the dilemma of how they coexist, etc. But definitely things were changing. And now I want to show you that. I want to show you that it wasn't just, the new universities which set the agenda for applied mathematics as we know it today. It wasn't. It was very much a collaboration between Oxford and Cambridge and their thinking and the problems that the civic universities were bringing to the table. And remember, the civic universities had money. They were powerful. They were very rich. And they could appoint chairs of applied mathematics in a way which was difficult in other places. So you have this interplay. Now let's just see musical chairs. Okay, let's start off with Bayer. Just to sort of prove my point, he was from a humble family from Saxony region. He showed great talent. He sort of was picked up, recognized as a draftsman, and then saw the opportunity, 21, to come to Manchester and make a fortune. He wanted to go in to become a draftsman in one of the locomotive factories, and his skills were recognized, but he couldn't because he was German, and the racial feelings of the time. It was very hard for him to be given a position over and above others. So he eventually formed his own factory, which was very successful, and then off he went. He made his fortune. He co-founded the Institute of Mechanical Engineering. He was a philanthropist and huge supporter of Owens College and the university. And there's one of his trains, and John will know what that is. Do you know what that is, John? What colour is it? So this is but this is actually from Canberra. This is a photograph. It looks like an oil painting or something. It's a photograph from about 2013 in Canberra. It's now in a museum there, but it's one of the Bayer, Peacock and Company engines, locomotives from 1887, I think. It's just soon after Bayer died. Is it a 440 class or something? Yeah, you know about that. Anyway, so they were highly successful. Let's move on to Arthur Schuster now. He was the one smoking the cigar, looking very dapper on the second left on the bottom. So his parents moved from Frankfurt to Manchester in 1869, bringing their textile business over. Okay, Schuster went to Owens College, studied physics and mathematics, And then there was this guy, Thomas Barker, who was a senior wrangler. So wranglers are very important. They're the top of the year. It's like a wrangler is like a first, and the senior wrangler is the person who gets the top first. And we'll give a big shout out to our senior wrangler in the room. I'm sure there's only one of them. So Chris Budd is here, senior wrangler. What an achievement. It's incredible. So he came to Manchester. He never did a blind bit of research after he got there, but he was a fantastic teacher and he taught loads of people. And Schuster got a good education. Then he went off and studied with Kirchhoff, Weber, Helmholtz. Fantastic figures in the history of applied mathematics. And then he went back and went to the Cavendish, unofficially, wasn't paid. And he studied with Maxwell and Rayleigh before returning to Manchester in 1880 and given the Bayer Chair of Applied Mathematics at Owen College. So in those days, physics, mathematics, applied mathematics, all sort of the same thing. They were all very capable. Then he moved to the Langworthy Chair in Physics in 1885, set up a new lab. And he was replaced in 1907 by Rutherford, who then went back to the Cavendish in 1919. So it really is. Okay, Osborne Reynolds, he was trained in Cambridge. And then in the age of 25, he was appointed the Chair of Engineering at Owens College. First position of engineering in the country. Off he went. And he remained there for the whole of his career. Fantastic career, father of turbulence. Great industrial and scientific significance. Amazing stuff. And the fact that Manchester could attract these people was because they had money, power. They had a vision for what they were setting up. Now the other way, J.J. Thomson, born in Cheetham Hill, so not far from where Mike and I were born and brought up, till 11, mile or two away, went to Owens College at 14, planned to be, a designer of locomotives, but for some reason he couldn't do it because his father died, but instead went to Cambridge. And he was second wrangler, which wrangled with him for the whole of his life that he wasn't first. And exceptional mathematician, but the Rayleigh left the Cavendish. He was a Cavendish professor, left. There was a vacancy and they decided that this chap is so brilliant, we've got to give him the position. And he just changed. He would have been an applied mathematician had he not got that position. And he got it ahead of Osborne Reynolds, who was, quite a bit older, had been at Manchester all that time, but they saw something. And of course, it paid off. He still has more students with Nobel Prizes than anyone else, I think. And look at those people that he studied. And Rutherford then came back after Thomson retired to take over the Cavendish professorship. And then here's the real hero, Horace Lamb. So born in Stockport. And then he was off to place at Queen's College, very brilliant young man, but he wanted to be an engineer. So he went to Owens College to improve his mathematics, but sort of more a broader education. Then he went to Cambridge, graduated, and then elected fellow, but he wanted to get married. In those days, you couldn't marry and be a fellow. Had to be celibate. So he left, and the only job he could get was in Adelaide, first elder professor. There were only 4 professors at that university at that time, and he got well paid, and he got paid all these people got paid by the student. So big courses, packed the students in. Okay, and he returned to Manchester, and it's interesting. There's lots of history about him returning to Manchester. And then 3 years later, he took up the Bayer Chair. What happened with this guy, Barker? Decided he'd had enough, so the pure mathematician left. So Bayer then took over that job, and then the professor in physics died. And so Horace Lamb decided that I can get the chair, and he turned it into the professorship of pure and applied mathematician. So it was teaching both, getting double the money. And he then sent Schuster packing off to physics, said, you can take that job there and I'll have the Bayer Chair off you and I'll make it the pure and applied. Okay, it's a good story. And he made many contributions, which I've not got time to mention. When he left Adelaide, they gave him this massive sort of plaque, all the students, and says something about they're not fit to sit at his feet or something like that. Anyway, so he was a brilliant lecturer, unlike Wiener stuff. And then there's lots of others, of course, in that story, some with connections to Manchester, some not. But, we have to mention Lord Rayleigh. He was the quintessential applied mathematician, I would say. And although he never came to Manchester, he was very influenced by that. He worked on lubrication theory. His work on acoustics, he wrote a classic 2-volume set. It really paved the way for the thinking in waves and acoustics and vibrations, more generally seismology, etc. And he took all the knowledge from optics, which is all about the heavens and God, and turned it into sound for problems with noise in industrial engines, etc. So he was very much drawn to problems which are of a practical nature. And then Lord Kelvin, some may say he's even more of an applied mathematician. He was brilliant. And you look how influential he was. Absolutely brilliant. Age 10, went to Glasgow University. And then his dad gave him the job, the chair of natural philosophy at Glasgow at just 22. They did try and find people, and then they couldn't. And then they in the end appointed him, and he was incredible, a really dynamic figure. And he was really interested in thermodynamics and heat, which brings us on to Joule, who's another northern hero. Joule was self-taught, an amateur scientist, very wealthy, son of a brewer. He was given the job of looking after the brewery, and he started to think about all these economic questions. Should I be converting to electric motors rather than steam engines? How much work am I getting out of the steam engine for coal I'm putting in, etc. And then he came up with this concept of the mechanical equivalent of heat, as they called it. It was about heat being a form of energy that you can transfer backwards and forwards from mechanical and other energies. And when you look at it, he was influenced because he was in Manchester by John Dalton, who was a propounder of the modern atomic theory. And so he thought about material fluids, if you're heating them up as little atoms, and then that atoms are gaining internal kinetic energy, etc. He struggled, but thanks to the support from Kelvin and others, Stokes and Faraday, then his views got accepted, and now it's recognized that he was right. And here's one of his little apparatus. It's a little paddle. So you have a little container enclosed with a liquid enclosed with the paddles on it. You drop a weight down so you know how much potential energy you're losing through the weight going down and how much must be gained in energy inside. And he gave very precise calculations to work that out. Okay. And then I'll just mention Heaviside, and I'm running out of time. So maybe I can pass, but I just want to say Heaviside was an unbelievable character as well. A nonconformist. He invented operator calculus, so Laplace transforms and everything, and simplified Maxwell's equations because he tried to understand them and made them much easier for everyone else. But he lived outside the sort of system, and he became very eccentric in later life. So I'm not sure how much time I've got, probably -2, but let's just talk about the present as very quickly as we can. So moving to the 20th century, we've got our model for applied mathematics. We've got the idea of what the subject area is about. It's thinking about maths, having tools, and then applying them. What's the areas? So we had all the role models. We had the universities. We had Oxford and Cambridge changing. We had the civic universities forming and changing, etc. But there was still a hell of a lot of animosity towards engineering and the more applied sciences even. So this is a Nature article. And you look at that, it's absolutely full of vitriol about these engineers. They can't get anything right. They don't define anything imprecisely. They're hopeless. They're not proper scientists at all. Anyway, then and then we come to the 20th century, and we know, as I say, the direction of travel was created by the Victorian mathematicians, and then G.I. Taylor was under J.J. Thomson, and he then moved into applied and became a really dominant figure in fluid mechanics, and his views on many aspects of fluid mechanics, stability theory, etc. We owe to him. Sidney Goldstein, James Lighthill, towering figure of applied mathematics, George Batchelor, Green on the solid side. They had really took that discipline as it had been identified and moved it on. And then the applications were sort of grew, meteorology, etc. But they were based on a continuum theory largely of the way things worked. They used lots of methods which were emerging: dimensional analysis, variational problems, asymptotic methods, and then increasingly numerical and computational. And the two world wars obviously stimulating the thinking, and then after the war, supersonic aircraft, weather forecasting accurately, etc. So we've seen it. And then this is the first couple of pages of the program for the BTMC, the British Theoretical Mechanics Colloquium, which is now the British Applied Maths Colloquium, which is taking place as we speak in Exeter this year. And Lighthill set it up. The first one was in Manchester in 1959 when he was just about to leave Manchester. And you can see, so that page I got from Tony Spencer. You'll remember him, the older ones of you. And he gave me lots of his old programs of the BTMC. This one was from Eric Watson, who was there. And you can see Eric's done a load of changes and made some notes. It's the second page. But if you look at the subject areas, you can see it's all that stuff that I defined on the last page. So very much continuum theories, nice application, some really nice theory, some methods, some computational, and lots of sort of bits of dirty stuff. But particularly like to point out this stuff here, which you can't read. But on the afternoon of the 8th of the April, they had visits to places. One was the Fluid Mechanics Lab at Barton, which Lighthill had set up. So he was very much keen on real-life fluid mechanics, doing experiments and validating your theories with the experiments. Another one was the Rayon Research Association Laboratory at Wythenshawe, said where fundamental research such as measurement of birefringence and of flowing polymer solutions is carried out. So stuff that John and Hilary are very, very expert on, this idea of man-made fibers and forming, the analysis of polymers and forming, the processes. And then the other one is the University Computing Laboratory. So Manchester was excellent at that time, of course, in computing, etc., and these other disciplines. But Lighthill clearly saw that industrial processes were very important. That's why he set up, or was the moving influence in setting up, the IMA in 1964. So here we've got these figures. I've just listed a few. And I've added on here that, of course, there were external influences, very heavy, strong influences. And really, I've just picked three here that I know about, but you will all have your favourite influence of how British applied mathematics was enriched by all these other subjects. Okay. Other groups around the world. So the changing world. And I have to mention Harold Wilson. I mean, the next big thing that happened was in 1963, he gave his speech about the white heat of the scientific revolution, white heat of technology or something. The need for us to reappraise ourselves. And, it was following on from C.P. Snow, who said that we're being led by a load of natural Luddites, that the place is full of government and ministries are all full of people who are all classically trained. We don't have enough scientists. We can still say that today. That's still an issue. How many scientists are there in the Lords or the House of Commons? We know that there's still an issue. 63 said that, and then led to the second wave of new universities. It was a very bold endeavour. Didn't have the same profound effect on society as the first, but maybe it did. Maybe I'm wrong. And then 64, Lighthill drove the formation of the IMA, and Alan Taylor and Leslie Fox initiated study groups with industry in 1960. And then for their sort of ideas, Alan Taylor and James Lighthill shared the first IMA gold medal in 1982 to make applied maths more impactful and relevant to the technological and scientific needs of society. It was very much focused on what we can do. And then John and Hilary, and John got the gold medal here in 2006. And many others, Colin, Chris, have continued the study group phenomenon, and then all the expansion of knowledge exchange and the Newton Gateway, ICMS's K activity, and the K Hub for Mathematical Sciences, which Chris Breward heads up now. They're trying to really connect us with industry. So I haven't really got time to discuss these, I'm afraid. But I was going to go through them and compare the past and the present. Okay, so maybe I'll just show the first one. We're back into a sort of pre-free trade era, mercantilism. It's having government control of a nation's economy to increase its wealth and power through maximizing exports over imports. Where have we heard that recently? Establishing colonies where you need the raw materials from the colonies and give you an overseas market. So that's the logic in what's going on around the world today. And the breaking down of international treaties. We want something, we want to get it, we've got the power to get it. So might is right, which is what plagued the world for centuries before we got to that sort of period in the 19th century and it was very wasteful. Okay, trade tariffs, as you see, it says in many documents, they're acts of war. Okay, immigration, global disorder, environmental health crisis, enormous problems. Do I need to even discuss them? We know what they are. Culture wars. So the culture wars are really important, aren't they? We know what's happening in America with the big, but it's happening here. The questioning of everything that we've worked for in terms of EDI, widening opportunity, ensuring that we consider other people and their views, maintaining healthy skepticism. So pushing us all down into thinking in one particular way or another. These are very dangerous and very anti-universities and anti-intellectual and anti-our community if we let it encroach. So we have to fight. Okay. We need to maintain a plurality of views. And then, this is my last slide. No, it's not, I'm afraid, but nearly there. Nearly there. So it was interesting. I found this article by Matthew Francis in The Guardian from 2013. So it's already 12 years ago. And that was celebrating like 50 years to Harold Wilson's speech. And he said many of the themes that Wilson addressed in his speech, higher education, lifelong learning, the balance between civil and defense research, promotion of innovation-driven economic growth, remains acutely, relevant today. It's even more relevant today than it was in 2013. Absolutely hit the nail on the head. Everything is so important. So from my point of view, we need mathematics to stop squabbling together. We need to come together. We need to broaden to encompass as much as we can. So we see everything out there as our domain, and let's go and try and investigate it in the rational and really successful way we have with all the tools available. Okay. Let's support the Academy for Mathematical Sciences, which will link maths education from first years through to retiring and continuing professional development. But we are ineffectual as a community. We're hopeless. And as was pointed out by Matt Butchers, the modern industrial strategy came out just 2 days ago. Not a word. Mathematics does not appear at all. Not at all. Life science is getting mentioned. Engineering is included. And they're thinking about how to upskill engineers. Why not us? We're critical to this. It's not just the engineers. We're part of that conversation. And the very fact we don't get in and have those debates is really our fault. It's a tragedy, and we need to not whinge because it doesn't have any effect, but we need to offer concrete suggestions. And they mention in it, drive innovation, capitalize on the value of UK data, enhance skills and increase access to talent. They're all the things we should be doing. And we do it. Let's just make a case more effectively. Okay. And then the AI elephant in my talk. I haven't mentioned it hardly at all other than that one mention because I don't know about it, and others in the room will know far more than me. But what we do know is something fundamental is happening, and it's the most fundamental change since steam, probably. Almost all jobs are under threat. So, the way we organize society can be both planned and executed by AI. So where do we fit? So in fact, it's like the CEOs who are most threatened by this than the people at the bottom. You may still have a job selling coffee, but not much else. So how do we ensure that we maintain society? Is not too disruptive, etc. How do we maintain social responsibility, international order? These are big questions, and maybe they're too big for us as a community on our own, but we need to think about those. And then I'm ending with this quote by Rena, who wasn't short of a quote or two, but it's very apposite at the moment because it's a mess and we've got to somehow make sense of it. So the sense of tragedy is that the world is not a pleasant little nest made for our protection, a vast and largely hostile environment which we can achieve great things only by defying the gods. And you can fill in who the gods are here. And this defiance inevitably brings its own punishment. So in trying to make change for the better, we can make things worse, etc. So I'll stop there. Thank you.